Hello everybody, this is the last lecture video about Module 3D. Thank you for coming to this video. For last three lectures, so we already discussed about what are the major parameters to design of seawater desalination plant and key terminology used to describe the membrane process, essential water quality, reverse osmosis, and today's lecture is about how to utilize the software, which is Water Application Value Engine, just called WAVE. So when you design your RO plan, so you need a very basic information. So we can start from manual because manual prediction is always a starting point, and then we can go for the complicated RO plan design using software. So just in case, to minimize your mistakes, so we have to have a general knowledge and skills to manually design the RO plans. So we need to know what size of your plant. So cubic meter per day you can decide, and feed water quality. If you don't know very detailed specific ions, so we need the general compounds, total dissolved solid, or osmotic pressure, and membrane properties. If this is the brackish groundwater or seawater desalination or wastewater reuse reverse osmosis membrane. So depending on your design of RO plants, so we can decide which membranes are available in the market. So all the informations are available, so we can select what is the average permeate flux and what is the salt rejection rate, and then what's the operating parameters such as feed flow rate and recovery rate. So this is the basic parameter for design. So let's go for the so this is the one example for wastewater reuse plant RO design. So let's assume each train has a capacity of 300 cubic meters per day. Let us use WAVE to size the RO feed pump for one train. What conditions do you use? And calculate the number of pressure buses, elements per pressure bus, total number of elements. So this example is very much similar to your assignment 3. But just the difference is the feed water quality, which is the wastewater reuse. In general, the wastewater reuse, we utilize the brackish water 3400 membrane from Dow Chemical, Dow Fintech. So we can select this one, and feed water, it's a secondary sweet effluent. TDS is 1800 ppm. Water temperature 25 degree. So production volume is 300 cubic meter per day. So we need to design this kind of membrane squid, pressure vessel and pump, and some of the stage pass, how many pressure vessels required, elements. So let's go for what's the reverse osmosis system analysis. Before we utilize the software, so basic concept, how we start from this. So we have 10 steps. First step is consider feed source, feed quality, feed product flow, and required product quality. Second step is select the flow configuration and the number of passes. The third step is select the membrane and element type. And step 4 is select average membrane flux, design flux. Step 5, calculate the number of elements, calculate the number of pressure buses needed, and select the number of stages, select the staging ratio. And the last step is about to balance the permeate flow rate. So we just follow these 9 steps one by one manually for the initial stage, and then we can go for more detailed software development oriented. Step 1. Consider feed source, feed quality, feed flow, and required product quality. The membrane system design depends on the available feed water and the application. The system design information and the feed water analysis should be collected first. So if you want to have your design of RO system, you just first go and get your target water, and then you can just give analytical center of water quality, and they can easily measure some basic parameter such as choose feed water source. So well water with STI less than 3 and surface water with less than STI 5. So STI already we discussed in our first lecture videos. So this is about what's the water quality in terms of particle, which can reduce your RO membrane fouling. And second option is to choose overall feed water concentration in TDS or individual specific ions. So if you have overall TDS, you can calculate the osmotic pressure. If you have individual specific ions such as calcium, magnesium, silica, sodium, chloride, sulfate, alkalinity, hardness, so we can have a better water inorganic scaling impact. So if you have an individual ion, you will get the better outcomes from your software design. Individual ion concentration from water analysis is always preferred. Second step, select the flow configuration and number of passes. The standard flow configuration for a membrane system is flow, and where the feed volume is passed once through the system. An RO system is usually designed for continuous operation, and the operating conditions of every membrane element in the plant are constant with time. A permeate stage double pass system is the combination of two conventional RO systems where permeate of the first part becomes the feed for the second part, which will increase our overall water quality to use second pass, third passes. So we decide which flow configuration number. And step 3, select the membrane element type. Elements are selected according to feed water salinity, feed water fouling tendency, required rejection, and energy requirement. The standard element size for systems greater than 2.3 cubic meter per hour is 8 inch in diameter, which means 1 meter diameter, and 40 inch long, 1 meter long. Very typical way of RO element. Smaller elements are available for smaller systems. So when you design less than 2.3 cubic meter per hour, so we can utilize 4 inch or 2.5 inch diameter of elements. For high quality water application where very low product salinity is required, ion exchange resins are frequently used to polish out permeate. So if we have still high concentration of your salt in the permeate, so we can also utilize the ion exchange resin to completely remove your minimum concentration of your salt. Sometimes, rather than using second pass, just the resin absorption is much cost effective. That's why some people select ion exchange resins. So let's look at the membrane type: TW, XLE, PW, SW, SWHR, NF. So NF is nanofiltration, which you can apply less than 1000 mg per liter of feed TDF. Seawater, SW, high rejection, SWHL. So you can apply from 10,000 to 50,000 mg per liter. Seawater, which almost SW membrane 3,000 to 15,000 ppm. PW is less than 5,000 ppm. Also XLE, brackish groundwater, or TW less than 5,000 ppm. Also depending on your water flow rate. So if you have more than 2.3 km per hour, we can select 4-inch element, and more than 2.3, 8-inch element. So depending on your size, so we can select different system permeate flow using different membrane element, and then permeate quality in general you will get less than 50 to 500 ppm. So we select membrane and element based on your size of the capacity and membrane type, water quality, and next step is select average membrane flux. RO systems are usually designed for a specific permeate flow rate, liter per hour, and the specific system recovery. These numbers and the specific feed water source are the information required to estimate the number of membrane elements, the membrane pressures, and stages as flows. And then we can select the design flux in terms of RMH based on the pilot data and customer experience, or the typical design fluxes according to the feed source from membrane system design guideline. So based on your water quality, and then we can select the element. So this element also provide average membrane flux, which is different from groundwater, wastewater, seawater, surface water, and we can select recommended average membrane flux. So this will be given by the membrane manufacturer companies. So each membrane has recommended average membrane flux, and then we can select based on each desired membrane water. Next step is to calculate the number of elements needed. The total number of elements needed is equal to design permeate flow rate over design flux over active membrane surface area of selected element. For 8-inch element, model number indicates active membrane surface area. Tau FIMTech, already mentioned about BW3400 element, has 37.2 square meter of active membrane area. So this is already given number, 37.2 square meter. And then what's your design flux? 20 nmH. And what's your total amount of permeate flow rate? Let's say 200 cubic meter per day. So based on the unit conversion, you can calculate how many elements needed for your total water. Then we can calculate the number of pressure buses needed. Total number of pressure buses needed is equal to total number of elements. So we calculate total number of elements, let's say 70 over number of element pressure buses. In general, in one pressure bus, 7 elements. So which means number of elements 7. Total number of elements are 70. So that we need 10 pressure buses to design this size of water capacity and round up to the nearest integer. For large systems, 6 element buses are standard, but buses with up to 7-8 elements are available for smaller and compact systems. Shorter buses may be selected. Although the approach described in the following section apply for all systems, it is especially applicable for 8-inch systems with a large number of elements and pressure buses, which then can be arranged in a certain way. Small systems with only one or a few elements are mostly designed with the element in series and a concentrate recirculation for maintaining the appropriate flow rate through the feed brine channels. So we can easily calculate this pressure buffer if we know what's the number of elements and then total number of elements in. The next step is to select the number of stages. So we have two options. First one is number of stages of brackish water system for wastewater reuse. Number of stages of seawater system for seawater desalination. And let's look at this system recovery: 40 to 6%, 70 to 80, 85 to 90% recovery for your wastewater or brackish water. And number of serial element positions: 6, 12, 18. So in this case, when you increase your recovery, you increase your number of serial element position, and then your stages at 6 element buses will increase. So you have a high recovery and then you have a high stages. So when you recover 85 to 90%, we need 3 stages. But if you just need 40 to 60% in brackish water, only 1 stage is enough. Let's see seawater desalination. So this seawater desalination has a very high concentration of initial salt. So recovery is relatively lower than brackish groundwater or wastewater. So system recovery 35, 40, 45, 50, 55 to 60%. Number of serial elements increased: 6, 7 to 12, 8 to 12, 12 to 14. And number of stages at 6 element buses we utilize first stage or maximum second stages. Number of stage for 7 elements, you can utilize one stage for 45%, 50%, possibly second stage, but 45% also second stage possible. And when you have 8 elements, so you can design this 45-50% first stage for seawater desalination. In general, when you design for your assignment, you may consider 45 to 50% of your recovery, and then you can consider second stage of your number of stages. After that, we can decide how many staging ratio required for our RO system. For a system with 4 buses in the first stage and 2 buses in the second stage, the staging ratio is 2 to 1. A 3-stage system with 4, 3, and 2 buses in the first, second, and third stage respectively has a staging ratio of 4, 3, 2. In brackish water system, staging ratios between 2 subsequent stages are usually close to 2 to 1 for 6 element buses and less than that for shorter buses. In 2-stage seawater system with 6 element buses, the typical staging ratio is a 3 to 2 ratio. So depending on how many pressure buses you have, so we can select 4:3:2 ratio or 2:1 ratio or 3:2 ratio. So it depending on your recovery, your pressure vessel number, so we can decide how many staging ratio required for our. Last but not least, to balance the permeate flow rate. The permeate flow rate of the tail elements of a system is normally lower than the flow rate of the lead element. This is a result of the pressure drop in the feed and brine channel and the increase of the osmotic pressure from the feed to the concentrate. The ratio of the permeate flow rate of the lead element and the tail element can become very high under certain conditions. High system recovery, high feed salinity, low pressure membranes, high water temperature, new membrane. So depending on the different conditions, also we have to carefully design how to balance your permeate flow rate, concentrate flow rate. Otherwise, you cannot achieve your final recovery and then effective water quality. The goal of the good design is to balance the flow rate of elements in the different positions. This can be achieved by the following means: boosting the feed pressure between stages, so you can have a consistent pressure without any pressure drop from first stage or second stage. Prefer for efficient energy use. Apply a permeate back pressure only to the first stage of second stage system. Lower system cost alternative. Hybrid system use membrane with lower water permeability in the first position and membranes with higher water permeability in the last position, namely high rejection of seawater membrane in the first and high productivity seawater membrane in the second stage of a seawater RO system. The need for flow balancing and the method used to Balanced flow can be determined after the system has been analyzed with wave. So wave is one of the tool because we cannot look at all the detailed water flow by manual calculation. That's the reason why we need to rely on software computer-aided design. So wave is the good strategy to design for our reverse osmosis. So this slide shows the example of manual design of the RO module. So basic conditions are feed water source, brackish surface water supply, STI less than 5, and required formula 8 flow is 720 cubic meter per day, and 6 element pressure passer to be used, and 75% recovery. So we can go for step by step based on this minimum condition. So brackish surface water with SDI less than 5, so total flow rate 720, and then Flux flow step 2, and step 3 select the membrane PW 30 element. PW element has active layer of 33.9 square meter, and recommended average flux for surface supply water feed with SDI less than 5 is around 25 mmH. So these two values are provided by the manufacturing company, and total number of element is 720. Total permeate flow 41.67, and just change the unit conversion, and 33.9 square meter of membrane surface area, and this is the average water flux. So total number of elements is around 35, and this pressure vessel number is 35, so 6 element pressure buses. So we have 6 divide, and then 5.8.3, so we need 6 pressure buses. Number of stages for 6 element buses, and 75% of recovery. So we need 2 stages to recover 75%. And last step, staging ratio. So we have 6 pressure vessel numbers, and we can select 2:1 ratio, which is 4:2 pressure vessel ratio for our module configuration. The chosen system must then be analyzed using the wave computer program. So we can put this page value in the computer aided program, and then this will provide a better result in terms of water quality variation, flow rate variation, balanced permeate and retentate. This program calculates the feed pressures and permeate quality of the system, as well as the operating data of all individual elements. So it is then easy to optimize the system design by changing the number and type of elements and their arrangement. So based on these steps, wave software, so you can install your program, and first screen is like this. So you have file, you can save and open the file, configuration, what's the flow in terms of different unit, bar, degree, and RMH. So you can select your very familiar unit conversion, and user settings, feed setup, report, and help. And also you have some other function for the pH adjustment, adding chemical, what's the compaction, ROTOC rejection, and home, feed water, reverse osmosis, and then summary report. So this is the 4991 seawater wave example, and you can put your feed water, and then you have a final product water. So how much water you need to produce, and water type is seawater, brackish water, wastewater, surface water. You can select from this tab, and there is a technology tab. So you can select pretreatment, ultrafiltration, reverse osmosis, ion exchange membrane, ion exchange resins, and you can also add some split and mixing point. So sometimes you don't have to pass through all the your permeate from RO to ion exchange resin, because you don't have to be too clean water quality. So in this case, just split your water flow, and then you can design. So if you see the more detailed tab, this is the first screen, and then if you click this one, feed water, reverse osmosis, and summary report can be analyzed from this. Let's go for next tab, feed water. So if you click the feed water, and it shows what's the system 1, 2, blended composite, and water type, and what's your SDI, and water subtype with conventional pretreatment, ultrafiltration. So you can select that, and solid content turbidity, and total suspended solid, SDI. So this is the all you have to analyze as water characteristics, organic concentration, temperature minimum, design maximum, and then this will provide 7.99 pH, and you can have your individual ions. So ammonia concentration, magnesium concentration, barium concentration, anion, your carbonate, bicarbonate, also chloride and sulfate concentration. So if you put all the concentration, this will provide automatically total cation, total anion, total dissolved solid. So 46,000 milligram per liter, which is the very high concentration of seawater in general. Like Middle East, the Gulf seawater has this kind of high concentration of seawater quality. Also neutral charge of your individual compounds. Boron is the one of the problematic compound, which can be very difficult to remove using RO, because this is neutrals, easily pass through. So based on this water chemistry compound, and next step we can go for reverse osmosis. So we can select first pass, second pass. So we can design first pass first, and first stage, and you can see the number of stage, how many stages do you need for the first pass, first stage, and second stage, what's other stage, flow factors. The flow factor is about your membrane fouling tendency, which means you have new membrane, you have a very high flow factor 1. But if you have old membrane, like after 1 year, 2 years, 3 years, the membrane flow factor will decrease. So we design for 0.8 or 9 for average, because lifetime of our membrane is almost 5 years for seawater desalination. And then we just put the flow factor is around 0.9, temperature average is 28 degree, and pass permeate back pressure and your flow. So feed flow 55,000 cubic meter per day. We need the recovery 43%, and you will achieve the permeate flow. And what's the flux of your membrane? Average flux, and then concentration, recycle flow, or permeate split flow. So based on your design flow, you can enter your value. And first stage, you can calculate how many pressure vessels required per stage. So based on this flow, and then we need around 280 pressure vessel, and number of elements per pressure vessel 7. And then we can select the seawater desalination high rejection membrane, which is the average water flux 16.5 RMH. And then we can select. Also, we have a different membrane, and this will also give you a little bit more specific information. And feed water goes, and then depending on your flow, also you can design pass 2 as well for the configuration of pass 2, and you will have a similar value also you can enter. And then feed goes there, and this is the permeate and second pass. So this is the second pass water, and then permeate following. And then second pass can concentrate can be mixed with the feed water again. So based on this kind of your permeate split flow, concentrate recycle flow, so we can design your system configuration using this reverse osmosis step. So to minimize the concentration polarization, permeate flow rate below upper limit, and element recovery should be below upper limit, and then concentrate flow rate above lower limit. To avoid the physical damage, feed flow rate below upper limit, and then this pressure drop below upper limit, and feed pressure below upper limit, which means if you have too high pressure, you will have a telescopic effect of your RO elements. So we have to make sure always the maximum limit has to be below to apply your feed pressure, even pressure drop, and then feed flow rate. Using our software, check the following feed flow rate per vessel in first stage 8 to 12 cubic meter per hour, concentrate flow rate more than 3.6 cubic meter per hour. So individual element recovery between 8 to 14% can be achieved for your system configuration. And based on that, also we can design pass 2. So pass 2, this is the number of stages. We want to use 2 stages for the pass 2. This is pass 1, already we designed. This is pass 2, and then we can also have a different flow rate, concentration, how much bypass, concentrate, flow rate has to go to the feed water, how many stages, number of pressure vessel, number of element for pressure vessel, so membrane type, because this is already permeate of your first pass, so your concentration of salt is very low, so we select brackish water 30H440 membrane, which is the 32.9 RMH water flux, and this is the another value we can just fine-tune this RO configuration, and then you can go for the summary report. report. Okay, before you click the summary report, let's look at our chemical information. So if you click the chemical, so you can have some change of your water chemistry. As I mentioned, pH 8 is the original seawater pH, but we put the hydrogen sulfide and we can have pH lower to 6, which will reduce our overall inorganic scaling, also degassing. So CO2, this is not for seawater desalination, but sometimes saline groundwater contain very high concentration of CO2 and carbonate, so we can utilize the degassing method to remove the CO2 concentration for desalination. So this will have a better desalination process. Also pH after post-treatment, we can increase anti-scalant based on our water chemistry, such as LSI, Steve, or some of the compound. We can also add some anti-scalant. So already maybe mention about the anti-scalant. The sodium hexaphosphate can be added for anti-scalant. Also dechlorination before the RO membrane, we have to remove the active chlorine, and then dechlorination, SBS, sodium bisulfite, can be added for this dechlorination. And you can see when you change temperature and recovery and different water chemical dose, so you can see the detailed information. So what's the measurement parameter? pH, LSI. So let's look at the pH first. Before adjustment, the seawater pH is around 8, and after pH adjustment we can put 6, 10 RO parts concentrate. After that you will have around 9 pH. So this red color shows some of your fouling potential. Calcium phosphate will be a very serious, calcium fluoride and magnesium hydroxide, also LSI. So what's the LSI? All of them are red color. So red color means this is warning sign, so that you have to keep changing your pH, or you have to add anti-scalant, also dechlorination. So based on also you have to change the recovery. If you have a very high recovery ratio, so you will get the high fouling inorganic potential. So we have to change this kind of so let's look at the LSI. LSI was all warning sign. So what's the meaning of this LSI? This is the carbonate scaling potential can be predicted by LSI, Langelier saturation index, scale potential. Negative less than 0, no scale potential. So if we look at the previous slide, it was 1, 1, and 10. So we have a positive value, which means you will have very high scaling potential. Calcium carbonate may occur. Close to 0, borderline scale potential, water quality and temperature change, or evaporation could change the index. So inputs: alkalinity, calcium carbonate, calcium hardness, and total dissolved solid, and actual pH and temperature to calculate this LSI value. So LSI is equal to pH minus pHs. Here pHs means 9.3 plus A plus B minus C plus D. Here A is the function of your total dissolved solid. B value is your temperature function. C value is calcium concentration. T value is the alkalinity concentration. So based on this ABCD and function of temperature, TDS, calcium, alkalinity, so you can predict your inorganic scaling, such as this kind of scaling will be formed on the membrane surface when you extract only pure water, and then your concentrate will be higher in the outer membrane. So we have to make sure we add some of anti-scalant, or we can reduce your pH, and this is the way. So if you have a pH lower, RSI value will be relatively lower. If you have a high pH, and then this RSI value would be positive, greater than 0. So depending on the pH, TDS, temperature, calcium, alkalinity, concentration, so we can try to lower the calcium carbonate scaling potential. So this is the last step, summary report. Our summary report can be calculated. So this is our design schematic diagram. Number 1, 2, 3, 4, 5, 6, 7, and 2A, 2, 4A, 4, 5, 6A. And you can see all the number, how the water quality changed, how they changed the different flow rate and pressures. So we can see the detailed report from our design of the system configuration. So low water feed to RO system, flow rate is 72,000 cubic meter, TDS 46,000 milligram per liter, and this is the 2A position. And what's the position 4, 6, 7, what's the different flow, TDS, pressure and flow, and can be obtained. And RO system overview. So when you design the different trains, and then net feed and net product, and then this RO recovery, and we have different paths in terms of water type and the feed, TDS, flow factors, and temperature, pH. Path 1, how this value changed. Path 2, how this source value changed, the overall system recovery, and then specific energy. So how much energy we consumed from this information. And you can also have a RO flow table. So when you have a 1F, 1R area, the elements we utilize this membrane. Pressure, bustle, how many we have in pass 1, and element for pressure, bustle, and feed flow rate, feed recirculate flow rate, feed pressure, boost pump pressure, and so concentrate flow, concentrate pressure, and pressure drop. Also permeate. So permeate flow, average water flux, and permeate pressure, and permeate TDS can be obtained. Also, we can see very detailed solute concentration. So already we input the different individual ions, ammonia, magnesium, barium, carbonate, bicarbonate, chloride, sodium, boron. So let's look at the boron concentration. In seawater, boron concentration was 5 ppm. After adjust pH and then same, and then concentrate, we have around 7.24 boron concentrate. And permeate, still after pass 1, the permeate concentration is almost 0.5 the stage 1F, and stage 1R 1.2, and total to pass 2 is 1.24. So this concentration is still high for the drinking water standard. It has to be around 0.5 milligram per liter. So we need to go through the second pass to reduce and this is the RO design warning. So based on the flow balance, permeate flow, retentive flow, and then all the balance can be calculated, how many elements every water is flowing very well, and then design warning can be found, what could be the information there. And this is a stage and the recovery for each element and the flow rate. So all the information for the TDS concentration can be found from this RO flow element level. Also second pass, as I mentioned, second pass can be also exactly the same, how much feed water quality is coming, and then how much permeate quality we can achieve. So 45,000 milligram per liter of salt after second pass, so we achieve 3.1 ppm, and stage 2 8.34 salt concentration. Also second pass, also individual ions, what's the concentration? Feed was 1.24 after first pass. Then after second pass, concentration of boron 0.1.2 ppm, which is very good quality of our drinking water standard. So this is the basically we can see all the detailed rejection and the individual ion behavior. Also we can see the solubility warning. So when you increase the 41% of recovery, and you can see what's the warning sign, stiff LSI value more than 0 positive in this second pass. Then stiff first pass, magnesium hydroxide second pass, anti-scalant may be required. Consult your anti-scalant manufacturer for dosing and maximum allowable system recovery. So there are several options whether we increase the concentration of anti-scalant or decrease the pH, or we can just reduce the water permeability, and the recovery can be reduced to avoid this inorganic scaling impact. So all the red colors showed some of chemical warning information. So you can, based on this information, we can think about what could be the best way we can reduce the inorganic scaling from this summary report.